page 14 or 15, something like that, all the restaurants within a 4-block radius. So as you're looking for food, looking for lunch, maybe tomorrow or dinner tonight, all the restaurants are listed there with phone numbers in case you got a large group and you need to make a reservation. Actually also lists whether it's breakfast, lunch, or dinner, so that you can, okay, just got to keep talking, blah, 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 blah. Oh, we're rolling, okay. And just a couple of quick announcements. I think the Root Wars game should be getting going in full force, so if you guys want to test out your hacking skills, you're certainly welcome to do so. You don't have to be chained to a table the entire weekend. You can play for as long as you want, jump in, jump out, and because it's wireless, you can actually hop on from, you can sit in here in this room, listen to the lecture, and hack away to your heart's content. In fact, a challenge might actually be to get on the AP without their knowledge, so maybe get bonus points for that. And we do have some spots left on the Monday workshop, the wireless workshop. Bunny's workshop is entirely sold out and has been, but we're offering full-day workshops on Monday that they're hands-on intensive classes where they're actually discussed in one of the last pages in your booklet, and I can actually give you the page number real quick. So there are just a few slots left on page 15 where they discuss the building/hacking open source embedded wireless mesh routers. So if you're interested in that, please see the front desk. And right now we've got Adam Young up, who's going to be talking about experiments from the cryptovirology labs, and let's give it for Adam.
Thank you very much. So today I'm going to be presenting some experiments that I conducted with Dr. Modi Young, who is a research scientist at Columbia. He's not a faculty member there, but he's had an office in the Department of Computer Science there for years, and he's a full-time employee of RSA Labs. Modi and I have had a very long, very fruitful relationship. He was my faculty advisor at Columbia, and we've been working on cryptovirology for over a decade now. So really what this talk is about is it's really making the transition from theory to experimental science. There are a lot of skeptics out there who really, if they don't see code, they don't believe it. They may think it's just a lot of theorems or hypotheses and maybe not a lot of weight behind it, but that was kind of the purpose of making this next step. And also, as any research scientist would tell you, very often you'll learn at least something non-trivial in the process of coding up something and experimenting. Sometimes it's a new idea, new theory, new algorithm, new protocol. Sometimes you realize, you screwed up something in your conference paper on it. So it's a very worthwhile endeavor to really just finally compile some of these things and have a look. So I'm going to back up a little bit and just kind of explain a little bit about cryptovirology itself. So what is cryptovirology? Over the years, you have seen a whole plethora of responses to this word. Most people, when they hear it, they think it's some sort of media buzzword, some sort of new craze to help sell security software, or some word that just sounded neat that doesn't really mean anything. And that's really not the case. It really is a growing area. Every year, more and more research scientists get involved in this. So from the FAQ, the cryptovirology FAQ on worldwideweb.cryptovirology.com, it's really defined as the study of the applications of cryptography to malicious software. So a lot of fields, may cross over. Some work in crypto crosses over into EE, some work in crypto crosses over into mathematics, etc. Cryptovirology really has its right foot in modern cryptology and its left foot in the theory of malware. So it's a definitely a crossover discipline. Attacks in cryptovirology are designed to give malware enhanced privacy, make malware more robust against reverse engineering, give attackers enhanced anonymity while communicating with their deployed malware, improve the ability to steal data via malware, improve the ability to carry out extortion via malware, improve the ability to carry out denial of service, to implement fault tolerance and distributed malware attacks, etc. So it really attempts to take a rigorous approach to designing malicious software. How old is it? Well, it's really kind of two answers to that. Under the heading cryptovirology, it's a little over a decade old. Modi and I published paper on cryptovirology in 1996, which I presented at the IEEE Symposium of Security and Privacy. So that was really kind of our first dive into this area. And what that paper was all about is cryptoviral extortion, using a virus to hybrid encrypt the files on a victim's machine and demand a ransom in return for files that they thought they had access to. And the non-trivial facet of that was the use of crypto. The malware before that had relied on symmetric crypto. Results on cryptovirology have been published in many of the world's leading computer science conferences, such as IEEE Security and Privacy, Crypto, Eurocrypt, AsiaCrypt, Financial Crypto, ACISP, ICICS, WORM, which is a pretty new conference now, the Information Hiding Workshop, and others. So really, it's an academic discipline in that respect. And despite how new it is, really, there have been enough results on this to write a book about it. And this book, I should say, reaches back into some of the ideas that date back to the 70s with Gus Simmons, who pioneered subliminal channels, which is an area that's kind of subsumed by cryptovirology. So this is a book I published with Modi about 2 years ago. And it not only summarizes our own work in this area, but we really did our best to include all the related work and even some work that's not, that may not appear to be related, but in fact is included in this. And this was published with Wiley. And so usually after I start talking about some of these attacks, which really do get quite involved, very often people start scratching their head and they're kind of like, how on earth can you justify, researching this kind of stuff? It's kind of subversive. And the answer that Modi and I have to that is quite simple. We like to draw an analogy to the field of cryptology. So it would be asinine to just assume that the crypto systems we have right now are secure and go about our merry way, right? We don't assume they're secure. We assume that there may be something wrong. And in fact, a cryptanalyst's job is to try to break existing crypto systems. So we draw an analogy, a parallel between that and cryptovirology, okay? We do not perceive our computers and our networks as being secure. We assume that there may be vulnerabilities both inside and outside. And cryptovirology is in some sense a proactive anticipation of what people will do when they get inside, not if, because some programmer is going to screw up and they're going to enable some sort of buffer or something. So our starting point is, okay, our starting point is not, okay, how do I break into person X's machine? Our starting point is, let's assume we're already in there. What is the nastiest, meanest, most covert cryptographic malware we can put in there that will stay there and survive for years and give us covert information subliminally over time, things like that. So our starting point is, hey, we're already on the inside, what can we do? And so this talk is really covers 4 experiments. We have a lot of other work, a lot of other algorithms and protocols we could have done, but this seemed to be an appropriate subject for Toorcon. These experiments are all part of our forthcoming book, which we've now called Advances in Cryptovirology, but chances are the publisher may insist on a different name. And so the layout of the book right now is it's kind of structured as, a chapter on theory, a chapter on the implementation of that as an experiment, chapter on some theory, chapter on the implementation of that. And the chapter on the theory is not to the level of a conference paper, but it will have plenty of citations to them, and it will cover a lot of the nuts and bolts of it. Okay, so moving forward, the first experiment is an implementation of the payload for cryptoviral extortion. Okay, this is an implementation of it. This is, again, the attack where the malware hybrid encrypts files of the victim and expects the victim to pay to get his information back. The second experiment is an implementation of what we call perfect questionable encryptions. So this is a relatively recent notion. We did manage to squeeze it into our book that we published in 2004, but we knew that we kind of had to clean it up and work out the bugs and issues. And to conferences, which we did later on. Perfect questionable encryption is a really neat kind of tool in cryptovirology. And really what it allows you to do is it allows malware to steal data from a host system such that even if an antiviral analyst monitors the life of that malware from beginning to end in a debugger, trapping every single instruction, they cannot prove that it steals data. The third experiment is the implementation of a crypto counter. It's a relatively simple idea, first published by Jonathan Katz et al., who I believe is still now a professor at the University of Maryland. And the notion of a crypto counter is to enable malware to store integer counters that are always encrypted, that can be incremented without first decrypting them, so that they can store counts of such things as how often a user logs in, how often someone goes to eBay, etc. And in fact, it is possible to update the counter without decrypting it, and this maintains privacy over time in an untrusted computing environment. And finally, the last experiment is an implementation of what we call tagged private information retrieval, which is based on published, well-known ideas on what's called private information retrieval, PIR. And this one is really, people don't even really believe this one is possible. In a nutshell, this is an attack where a crypto Trojan is designed to steal the password and login of a particular user known a priori, no one else's. On the surface, it may look like a traditional keyboard logger that's built into, say, the password program or something like that, but it's really completely different. What it does is it filters all the passwords and logins that come in. It only takes the one of interest. When it finds it, it essentially public key encrypts that key pair. I mean, that password pair. But again, it has this quite amazing property that even if you watch this Trojan, every instruction it executes from its entire life and store core dumps all along the way, you cannot learn what login it is after. You can't learn what user it's programmed to target. And by the way, the hidden password file that it stores the asymmetric ciphertext to doesn't grow with time. It doesn't just keep lobbing on new ciphertexts of login password pairs. It's size and it's pretty small. So, okay. So let's move forward. First, you have to look at the animated GIF. I purchased these. No copyright violation. So I know they're kind of budget GIFs. So this is, what is cryptoviral extortion? Well, there's a new name now, a new fancy name, new buzzword, ransomware. You probably all heard this. Most people didn't realize quite how old this goes. It even goes way back to, the 80s. The AIDS information Trojan was somewhat similar in flavor, although that used symmetric cryptography. We define cryptoviral extortion as an attack that utilizes public key crypto in particular. And this is an active attack where the virus totes around within it the public key of the attacker as a constant. And it hybrid encrypts data files of the victim using the public key that the virus totes around with it. The attack only works if there are no backups of the data file. If there are backups, then they just zap the machine and reinstall from backups and they're fine. So that's an assumption. In this attack, the attacker demands some form of ransom in return for the randomly generated symmetric key that was used to carry out the attack. And this is a key that's generated at runtime when it actually attacks the files and encrypts them. Well, the ransom could be money, it could be data, it could be a lot of things. And what's wild about this attack is that even if you scrutinize the virus, even before or after the attack, you will not learn the decryption key that's needed to recover the files because it's a private key, which is not contained within the virus. So there are some assumptions for this attack. I already mentioned the first one. No, sorry, I didn't mention the first one. The first assumption is that the host machine actually contains data D that's valuable and that if it's lost, the victim will want to negotiate and pay for its return. Okay, so that's an assumption. And the other obvious assumption is that it's not backed up. And the next assumption is that the virus has access to a secure random bit generator. Okay, so a lot of operating systems provide this facility. Some are secure, in general, this can be construed as a facility that user programs have access to. It's assumed that the virus has access to a secure symmetric cipher, so either it brings its own to do the job or it uses an API call. And also it's assumed that the virus has access to a secure asymmetric cipher, such as RSA. Again, it can tote its own, or maybe it will make a Microsoft cryptographic API call or something like that. And so here's the attack in a nutshell. The virus writer generates a key pair, a public and private key. X is the private key, Y is the public key. Y is encoded within the virus. The virus is released. It spreads to, say, thousands of machines. And given a certain condition, maybe it's October 31st or Friday the 13th or something, the viruses activate. And what they do when they activate is as follows. Each virus generates a random symmetric, like a triple des key or an AES key. And it encrypts data D, the critical data, using that symmetric key. It then encrypts the symmetric key with the public key Y that's contained within the virus. So there are actually two ciphertexts. And this is hybrid encryption. Hybrid meaning it uses two different ciphers to perform encryption. Then what it does, the virus deletes D and it deletes the symmetric key. It zeroizes them. It overwrites with ones, zeros, ones, whatever's needed. And then it tells the user, you know, hey, you lost your data. If you want it back, here's the digital pseudonym or whatever. You know, contact the author and let's talk. Again, we kind of shy away from exactly how one would go about the anonymous communication. We always say, you know, you can use mixnets or whatever, but who really knows, you know, what exists today. Okay, and then, let's assume now that the victim is willing to negotiate for the release of the data. The victim provides the asymmetric ciphertext lowercase c, which is short, to the attacker. The attacker, and must give the ransom. Okay, assuming the ransom is good, the attacker decrypts C using his private key, lowercase x. Only the attacker can decrypt this, because only the attacker knows the private key. This reveals the symmetric key that was randomly generated at runtime when the virus attacked the files. And this symmetric key is sent back to the victim, and the victim can use it to decrypt data D that's encrypted using the symmetric cipher. So that's cryptoviral extortion in a nutshell. So what's the security of the attack? Well, analyzing the code will reveal the public key, not the needed private decryption key. As long as the symmetric key is not captured in RAM while the attack is being carried out, it will not be available to the victim. Okay, so if this thing does periodic core dumps or whatever, and he goes through his logs and manages to find the symmetric key in a core dump somewhere, then he. Okay, so that's one facet of the security. Also, you know, maybe it's a lot of data. So this attack can be carried out incrementally over time. The disk accesses can be merged using traps or whatever with the normal disk accesses or what have you. You know, standard methods there. And again, data can be extorted instead of money, and mixnets, etc., public bulletin boards type things can be used for anonymous communication. So, has such an experiment ever been conducted? And I don't mean actually, you know, extorting money from someone. I mean, has, you know, a software implementation ever been done on this? And the answer is yes. It was the subject, one of the main subjects of my master's thesis at Columbia University, where I ported the GNU multi-precision library in 1995 to Macintosh System 7.1. Yeah, I know, hey. I can be a systems guy too, you know. All the compiler errors, you wouldn't believe them. But I did it, and it worked. And I believe I implemented T myself, the Wheeler-Needham's tiny encryption algorithm for the symmetric cipher. And it ran, and we have all the statistics and stuff in our conference paper from '96. It's all there. Interestingly enough, you know, I just in the last 2 years, I looked back and I was like, well, gee, you know, when did Microsoft API first come out? You know, was it before I, you know, bashed my head against the wall doing this, or was it after? And based on what I was able to find on the internet, it was just a few months later, after we presented this in May in Oakland, that CAPI was released in Windows 95 OEM Service Release 2. So that was August. So it came out right after. And this was for Windows NT 4.0 and other operating systems. So really, this experiment was done or the big Microsoft Windows even had a cryptographic API in these operating systems. But now the really, to be honest, the terrifying thing is that Microsoft cryptographic API is in all Windows machines. And I say that as a cryptovirologist, not as I mean it's a great thing. It does help secure a lot of systems, but it's an incredibly powerful tool for doing this type of. Okay, so a full-featured cryptographic API, all you got to do is make DLL calls. It's sitting in everyone's System 32 directory. It's just there. Okay, so what I did in the last 2 years was I revisited this same problem, except I had a different approach to the experiment. The idea was to investigate how easy is it to do cryptoviral extortion today, right? And this was the very heart of an ISC paper of mine, which I presented in Singapore, which was invited to be a journal paper at the International Journal of Information Security. And so in that experiment, I implemented cryptoviral extortion again a decade later. And I found that all I needed was 13 types of Microsoft cryptographic API calls, only 8 types of which are in the payload, and about 72 lines of ANSI-C code. And these are comfortable lines. These aren't like, oh, lines. And you can do this attack. So in a nutshell, the type of crypto that we use from CAPI, and there are all kinds of algorithms in there, but the ones that this uses is 3-key triple DES, 168-bit keys, cipher block chaining mode for symmetric encryption. It uses a randomly chosen initialization vector, which is set using crypt set key param. It uses a 1024-bit key from the enhanced provider, and uses PKCS1 encryption and decryption, optimal asymmetric encryption pattern. So this is like state-of-the-art. This is stronger crypto than we did in '95. I mean, definitely by far stronger crypto. And it also uses SHA-1, but it uses that not in the payload, but it uses that to manage to secure the key pair of the attacker. So what's in the payload? What's in the payload is just these API calls here. I'm not going to go into them in detail. They're all on like MSDN or something like that. You can look them up. But basically, these calls are able to acquire and use the public key that's contained within the virus, generate a random session key, export a key or key pair from a cryptographic service provider into a key blob, generate random IV, encrypt byte stream, encrypt destroy key, destroys key, etc. These are the other 5 types of CAPI calls in the overall experimental implementation. Crypt decrypt performs the decryption, so this is done on the back end on the attacker's side. Crypt decrypt. This is done when the victim is recovering. And the four blue functions are used specifically to manage the RSA key pair of the attacker. So there's crypt create hash, hash data, derive key, and destroy hash. So what these functions are used to do is the attacker enters into this experimental program a password, and this transforms the password into a symmetric key, which is used to encrypt and decrypt his RSA key pair for the attacker. So that's why they're blue. Okay, so basically the overall protocol and the implementation is broken down into 4 functions. Four functions which is spread across 2 ANSI-C functions. So there's the ANSI-C function key pair owner, which takes either 0 or 2 as an argument. And there's the ANSI-C function plaintext owner, which takes either 1 or 3 as an argument. Key pair owner does RSA key generation for the attacker. Plaintext owner does hybrid encryption of the victim's plaintext, and this is the one that would actually be the payload. Key pair owner 2 does asymmetric decryption of the session key by the victim. This is done on the back end on the attacker's side. And plaintext owner 3 does symmetric decryption of the victim's file. So this functionality, plaintext owner 3, it could be included in the virus, or it's software that could be sent to the victim once he's paid the ransom to allow him to recover his stuff. So it really doesn't have to be toted around with the virus. Okay, so what is this? I'm not going to go over this line by line. But the significance of these 2 pages is that the payload fits on 2 pages. Right? So that's obviously the public key on top. And you can obviously see that's not the RSA modulus there at the beginning. That's obviously some sort of data structure. But if you follow it along, you'll eventually see 10001 in hex, and that is in fact the RSA public key to the 16 plus 1. Anyway, so that's the encoded public key for the attack. It's just a string constant, as you see. Okay, so that really sums that up. I mean, that was just the idea, was to really, revisit the problem and really try to measure in terms of number of API calls and number of lines of code exactly how difficult it would be for a programmer to do that kind of attack today. Okay, on to the next experiment. Might not get to them all, I hope I will. Perfect questionable encryptions. This one's really something. So the idea here is to address the following problem. To steal plaintext information from a host system using malware with the following desirable properties, if possible. Allow the attacker to obtain the plaintext without getting caught. Establish a private channel between the malware and the attacker to foil eavesdroppers. Establish a covert channel between the malware and the attacker to prevent denial of service of the malware channel. Right? So if they can't, if ISPs or whoever's doing filtering can't reliably detect this covert communications channel, they may get in big trouble if they just start killing signals. Right. And also to hide as much functionality to malware as possible, even when it is reverse engineered and or monitored at runtime. So we have a partial solution to this, which we published at IEEE Security and Privacy 1 year later in '97, and we call it deniable password snatching. And again, this was in 1996, 97. So we assume an attack that uses floppies, just as an example. So if you hear me say floppies, don't laugh. So the idea is as follows: you want to install a password snatching Trojan on a system. You physically walk up to it. Let's say it's an isolated system that's shared by users. You want to install a Trojan, they'll snatch passwords over time. You want to go back to it a week or two later, and you want to download these passwords. How do you do that without getting caught when you install it? You can get caught when you return and download it, right? Because maybe someone's going to install quiet monitoring software that will silently signal the security guy in the back of the office or whatever. So how do you do that? Well, this is one way, and this affords a lot of protection for the attacker. The attacker writes a Trojan that snatches password. He puts it in a virus. It is the payload of the virus to install the Trojan. So the attacker walks into this facility with a virus in a program, an infected program, on a floppy. And just when he sets foot in the facility, if he's caught with it and it's analyzed, he says, "Oh, I didn't know I had a virus. Sorry. I didn't write it. Usually I better scan my hard drive." Okay, so that's the idea there. So the guy runs it, on the machine, and runs the program on the disk, and the disk installs the Trojan, and then the Trojan's in there, and it starts doing its thing, and it goes home and just sits tight for a while. And what the virus does is, again, the virus installs the Trojan. What the crypto Trojan does is it uses its public key to encrypt the login password pairs that it sees during this time interval. It stores them in a hidden password file, but it uses a very specific data format for this password file. It uses a circularly linked list. And every time it adds the new asymmetric ciphertext of a login password pair to the list, it overwrites the element in the list. So it always contains the freshest set of user logins and passwords. And that's important. One of our goals is to not give away the presence of the Trojan. And to meet that goal, we ensure that the hidden password file never changes in size. Okay. So now we have this extra level of privacy too, because anybody who haps upon this hidden password file is just going to see a bunch of asymmetric ciphertext, and it will be indecipherable. The attacker's faced with the problem of going back, when his heart's racing on his way back, a little adrenaline, and downloading this hidden password file, right? Because he can get busted there. Maybe it was found. Maybe special hidden software alarms are now waiting for this criminal to return. Okay, but actually, with that problem in mind, the Trojan is designed to do the following. Every time a writable or media is put into the drive, and the last few sectors of this media are unused, the Trojan unconditionally copies the hidden password file to the last few sectors and leaves them marked unused. What does that mean? That means everyone who inserts a writable floppy into this gets the file. It's the difference of push versus pull, uploading versus downloading. So the guy comes back, he inserts a blank disk, he writes a letter to his girlfriend. What if he was busted doing that? Well, how can you bust him? That probably happened to 100 people over the last 2 weeks. That's all they did. So that's the idea, and we call this deniable password snatching. So he goes home, he busts out, Norton Disk Utilities or whatever. He carefully extracts these sectors, and then he decrypts them with the private key. And only he can do this, because only he knows the proper private decryption key. And this extends to network-based attacks and things like that. Okay, so again, all I really did here was review deniable password snatching, but this experiment is about perfect questionable encryption. So what's that all about? Well, we can improve the attack even more. And the idea is as follows. We want to obfuscate whether or not the Trojan is actually encrypting anything. Okay? I mean, okay, so it starts calling RSA, it makes calls to AES. While it's doing this, say if it hybrids encrypts the login password pair. At the very least, it needs to call an asymmetric encryption function like RSA. So you can watch it do that in IDA Pro or OllyDebug or whatever. So we ask the following question. If you take core dumps of this Trojan passing plain text and a public key to the asymmetric encryption algorithm, this is the public key within the Trojan, is it performing encryption? Is it theoretically preserving the login and password pairs of the users after this mathematical transform is applied? In other words, can you prove that the malware has been used to steal data? This has everything to do with the algebraic structure of the public key, which might be bogus. Okay, that's the idea. So here's the question kind of revisited. Does the malware code and core dumps of its operation prove that theft has occurred? Answer. Not necessarily. In any public key crypto system, the attacker can generate a key pair, throw away the private key, and have some witness that witnessed him throw away the private key. Then he's not getting a hold of the plaintext. So in some sense, one might argue he's not stealing it. Okay, so I'm not going to get into legal stuff here. All right, there's a huge problem with this. Obviously, what jury's going to believe? What jury's going to believe that this private key was actually destroyed? Okay, so that's kind of a stupid argument and that possibility. But let's ask the question again now with a different public key crypto system. Let's ask the question with El Gamal. Okay, so does the malware code and core dumps of its operation prove that theft occurred when the El Gamal public key crypto system is used? El Gamal has a very kind of crazy algebraic property that it's possible to sample public keys using the exact probability distribution and from the exact set as the way these key pairs are defined. Okay, it's possible to sample a public key randomly knowing the corresponding private key. Okay, you can choose Y randomly without knowing X. And that's a bit different than claiming it was throwing away. It's claiming that you sampled Y randomly and never knew X. Okay, but again, it's the same basic kind of problem. Who's going to believe that the attacker sampled Y without computing Y equals G to the X for some X that he knows, which is the El Gamal private key? Okay, so those are obviously very weak, but interesting sort of things to think. So Modi and I introduced the notion of a real versus a fake public key, and we managed to squeeze it into our book that we published in 2004. So we define a real public key as a public key that produces decipherable encryptions, a correct public key. We define a fake public key as one that produces information theoretically indecipherable encryptions with respect to everyone. There is no private key that can decrypt encryptions of such public keys. They're perfectly useless in some sense. But obviously they're not useless, otherwise I wouldn't be talking about them. So a real public key produces decipherable encryptions, a fake public key produces indecipherable encryptions. So the attacker chooses which one to put in the malicious software, real or fake. However, one of our requirements of a fake public key is that it looks just like a real public key. And that is a very specific meaning computer science. What we mean is that under a specific intractability assumption, there does not exist a probabilistic polytime Turing machine that can distinguish between a real public key and a fake public key. Okay, and that obviously requires proof. And our questionable encryption construction has the property that the attacker has the exclusive ability to prove whether the public key in the malware is real or fake, and he can prove it at his own discretion. Okay. So we presented this at, after we went over it in our book, we worked through some of the details. We presented it at MyCrypt in Malaysia, and it's now the subject of an IEEE Transactions Journal paper. Our construction is based on the Polyere public key crypto system, which has some really amazing algebraic properties. And so what our construction looks like is as follows. We add a brand new key generation to Polyere. We call it the fake key pair generation algorithm. And what it does is it produces a fake public key on output, and it also outputs what we call a witness of non-encryption, which is a poly-sized value that proves that the public key is fake and can't be used to decrypt anything. There's also, along with Polyere is three algorithms: key generation, encryption, and decryption. Polyere key generation is the real key pair algorithm. It produces a public key that produces decipherable encryptions. We add another function to Polyere in this construction, and it's a predicate function f that returns 0 or 1. And this function takes as input a public key and a witness. Okay, so the witness of encryption is the private key, a normal Polyere private key. Okay, so there's a fake public key and a witness of non-encryption, and then the public key, which is a normal Polyere public key, and then the Polyere private key, which is the witness of encryption. So the predicate f takes as input a public key and its corresponding witness, and it outputs 0 or 1. Okay. It basically decides whether the public key is real or fake. And also another security property for this construction is that it is impossible for a public key to be both real and fake at the same time. Okay, so the attacker can't take and eat it too. If the attacker puts a fake public key in the malware, and the malware is used to encrypt data and transmit it, the attacker cannot recover that data. Provably so, the attacker cannot recover that data. Okay, so the details of this construction are outside the scope of this presentation, but it behooves us to mention that this notion is related to but different from other notions in cryptology, namely oblivious transfer, all or nothing disclosure of secrets, and deniable encryption. So enough with all of these nitty-gritty details. Let's talk about an attack scenario. So here's the attack scenario. The attacker generates a real or public key. The attacker places the public key in the Trojan. The Trojan encrypts, in quotes, encrypts stolen plain text and covertly broadcasts it. If the public key is real, then the attacker reads the broadcast, deciphers it, and obtains the plain text, because he can. If the public key is fake, then the attacker can't read the broadcast, doesn't even try, and this is a form of spoofing attack in that case. So what good is this, right? In one case, he fails to steal data. Well, let's back up. Let's take the 10,000-foot view of this. Okay, suppose there are hundreds of people doing this, some of which use real public keys, some of which use fake public keys. A prosecutor cannot prove that the malware that transmits, that a processor cannot prove that malware transmits plaintext from the host computer system. How can they? The prosecutor must prove whether the public key is real or fake. Right? Burden of proof. Right? So that's really it in a nutshell. Okay. It may be possible to prove indirectly, okay, that this malware was used to steal data. Okay, so maybe the accused is, made 1,000 fraudulent credit card purchases, and there was essentially no other way that he could have obtained the credit card number, so you can infer indirectly that it came through the malware, whatever. There may be indirect ways. This cryptographic technology makes it impossible to prove directly that such malware steals data. An attacker may take the fifth and refuse to reveal the witness of encryption or non-encryption, whichever the case may be. And the basic idea here is that this attack can set a precedent that malware that appears to encrypt data and steal it, in fact, does not. Right? So maybe hundreds of people can do 75 of which use a fake public key. And after 2 years, after Symantec and McAfee and all those guys have studied these attackers anonymously publish the witnesses of non-encryption on bulletin boards somewhere. And then people execute it through the predicate function F. And they, in fact, verify that these are bogus public keys. They're fake. They could have possibly stolen from people who were infected with this virus. So it's even possible to set precedents, without a single court case in this kind of thing. So, okay, so we implemented this. The implementation is in ANSI C. It uses OpenSSL as the underlying crypto library. It uses the minimalistic GNU for Windows Development Suite. To do this, we implemented Polyere key generation, encryption, and decryption ourselves. OpenSSL does not currently have Polyere at all in it. We also implemented the predicate F and the fake key pair generator. And our experimental implementation is actually capable of encrypting full-on files. And it uses Polyere and also Blowfish in cipher block chaining mode. Okay, I'm not going to get through all of these. So I am skipping experiment 3. If any of you are interested in crypto counters, please see me. And now I'm just going to move on to the last one. Tagged private information retrieval. So one can think of two password snatching scenarios. An indiscriminate case and also a case that discriminates on which passwords we're after. In the indiscriminate case, we want everyone's password or no one's password in particular. In the case that discriminates, we want the password of a particular user. Obvious desirable properties for this are we want the hidden password file to be confidential, so that implies the use of asymmetric crypto. We want the Trojan to remain unnoticed, a fixed size hidden password file. And we want to hide the functionality or the purpose insofar as possible of the Trojan. Okay, I'm going to skip straight on to the discrimination case where we discriminate between which password we want. So in this case, we want the password of a particular user known a priori. We don't care about anyone else's password. And the critical property is that the Trojan must not reveal the user's identity while the Trojan is scrutinized at runtime. Okay, so now that's in red and it's in capital letters for a reason, so let me read it again. The Trojan must not reveal the user's identity even while the Trojan is scrutinized at runtime. This is a Trojan that goes after that user's password and no one else's, and that's our security requirement. Okay, we want a fixed size password file that's as small as possible, and we want a negligible probability of this Trojan missing the user's password if it happens to see it, receive it at the terminal when the user logs in. Is it possible to devise such a targeted password snatching Trojan and not reveal the login of the user that the Trojan is designed to steal the password of? The answer is yes, and it's extremely non-trivial, the construction for this. It's based on private information retrieval, which is a relatively new notion in crypto. It's about roughly 10 years old. I don't have time to review PIR, unfortunately, but I will go over the attack. The attack runs a query generation algorithm. He supplies it with the login of interest, and it spits out a query, which is a file. The attacker deploys this query file with the Trojan. The Trojan receives login password pairs. It runs the database administrator algorithm on these pairs as it sees them and updates the query accordingly. And this has the property that when the right login is seen, it is written to the query file, which then becomes the response file. But no other login password pair is written into this. And so this happens over time. Over time, finally it sees the user logs in. Now, one thing here is the user can't change his password. He'll actually break this system if the user changes his password. But assuming the user keeps the same password, this works. And then finally, later on, this Trojan will broadcast this query file, which is the response file, and the attacker decrypts it. And only the attacker can decrypt it because only he knows the needed private decryption key. And again, our claim is that if you analyze this Trojan throughout its entire life, every single instruction it ever executes, you will not learn the login that it's targeting. If you guys want, compile it and run it. There's the URL for this code. You'll have to, go through the process and produce your own fictitious login and password and do it. And again, these are experiments, so we encourage people to learn more about this and really just do it. Okay, here are the references. That's the one that really is very heavily based on the Ketchin, McCauley, Stadler paper from Eurocrypt 99. Okay, I guess do I... Oh, you want the URL. Okay. Well, I can tell you. Just go to cryptovirology.com and click on source code. But, here, I'll make this bigger. It's really, this is all really quite wild stuff. Oh, I can't see. Do I have 5 minutes for questions? 10 minutes for questions? I'm supposed to stop now, right? So. Oh. Show of hands, anybody think they're going to have questions? Let me see them all at once. Hold them up. Let's do questions. I think. Okay. Yes, go ahead. It does re-encrypt, but it never decrypts while it's deployed. No, actually, Polyere is what's called an additive homomorphic public key crypto system. Okay, so the plain text range is from 0 to n minus 1, where n is the product of two large primes. And actually, what you can actually technically add any number between 0 and n minus 1 to the currently stored plain text, and it will add modulo n. Okay, but in our implementation, I believe we just do increment by 1. And so what you do is you take 0, you Polyere encrypt it, and there's two algorithms you can apply to that. There's what's called probabilistic re-encryption, and then there's the increment algorithm, and we do them both. Probabilistic re-encryption is amazing. It is possible in Polyere and other crypto systems to re-encrypt a value without decrypting it. You apply this out. Anyone who knows the public key applies this algorithm. They produce a totally different encryption of all possible encryptions for that particular plain text, and it's correct in the decrypt algorithm. And the reason why that works is probabilistic encryption is one-to-many function. There's many possible ciphertexts for a given plain text. So cryptologists will view this particular version of crypto counting as trivial. But, you know, it's really cool applications. Does that answer your question? Yeah, I download the chapter. I think the chapter's already up. So, yeah. Well, that's not the crypto counting idea. That's tagged private information. So that's what we. Yeah, that's okay. Right, exactly. So if we go back to the slide, we're saying watching the counter doesn't count. Okay, so the idea is that obviously if you watch the counter count, you'll know it's x plus 47, whatever it was plus 47. You can't hide that. So. Yes, that's simply the probabilistic re-encryption function. You can do that ad nauseum, and you won't change the plain text at all, and it'll constantly look different. Yes. So every minute, you can do this. Every minute, you probabilistically re-encrypt. Every time they go to eBay, you add. Every minute, you probabilistically re-encrypt. Every time they go to eBay, you add 1. So. All right, or whatever it is, but I think you got the idea. Yeah. Any other questions? Yes. Oh, okay. Yeah, that's well. What Modi and I basically do is we ruin the generator. Don't think of it. constant G in Polyar. Okay. So G is supposed to have G can be G is a public parameter. It's part of someone's public key using. G is supposed to have an order that is a multiple of n. Okay. The G's that the fake Q pair generate have an order that divides lambda n, where lambda is common. Okay. So what that means is that you get a random nth residue time you encrypt with a fake key, which information theoretically means you can't decipher. Any other? Yes. I cannot answer that. Any other questions? Yes, Mike. You can subtract with the crypto counter. You can add and subtract modulo n. Yeah, it's modulo math. It'll wrap right back to that massive endpoint if you... Oh, no. Oh, boy. If you can get multiple, you get a full-fledged crypto computer. No, no, no. You get addition and subtraction modulo n. Additive. It constitutes an additive homomorphism. When you multiply two Polyar ciphertexts, you add their plaintext modulo n. It's wild. Any other? How long? 5 minutes. Okay, more questions? Yeah. I'm sorry, I didn't hear this. Writes my grants. Well, Diet Coke. Because I'm older. Okay. Used to be Coca-Cola. Another more serious question. Is that it? Yeah. You mean the traffic? Okay, that you kind of dive straight into steganology with that. So Modi and I use lots of notions in steganography. We kind of take them for granted. Okay, so and there's a lot of very deep work going on right now in steganography. But yeah, I mean, we can make the assumption that malware is able to get a candidate photograph or video or whatever and embed stuff and hopefully be able to hide it and stuff. We view that as an API for cryptovirology. And there are other people who know far more about steganography than I do. But I think you kind of had more of a stego kind of question. But, did that answer your question? Questions? That's it? Okay, thank you all very much. Yes.
Is there like a theoretical phenomenon on
Oh, right. Very well known.
so is like diversion a problem? Because you keep like doing it, and then at some
Your
point,
chances of it. Yeah.
we didn't come up with the term.
Yeah. No, right. I think that was hey, that's cool, You say tomato, I say tomato.
It's getting a lot. Actually,
Yeah. Oh, has it? Really? Yeah. Cool. When you multiply two Polyar ciphertexts, the corresponding plaintext add modulo. No. No, it is semantically secure against plaintext add. I would read Polyar's original paper on it. Yeah, absolutely. There have been a lot of follow-on papers to it that look